All right, I'm back. We are on page 324, and what we're going to do now is we're going to use calculus to graph some things. So we're going to start off with things we already know, because then we'll know if we're getting them right, and then we'll move on to things that maybe we're a little less certain of. So let's see what we can do. So the first one here is we're going to sketch a quadratic using calculus, which seems ridiculous, but at the same time maybe isn't that ridiculous, right? Because we have all these new skills. We're pretty sure we know how to use them. But if we apply them to this and then it doesn't work, then maybe we don't actually know what we're doing. We should go back and review some things. So let's see. So I'm going to start off with f prime. So f prime power rule, 2x minus 4. F double prime power rule again, just get 2. So this is actually kind of a weird scenario where if f prime equals 0, I get x equals 2. F double prime never equals 0. F double prime, in fact, is always greater than 0, but that's all right. We can still number line this thing. So sign chart, put 2. This will be for f prime. Sign chart, put nothing. That'll be for f double prime. Okay, so f prime to the left of 2, negative a billion, is definitely negative. And then to the right is definitely positive. F double prime is just 2 all the time, so that's always positive. Positive, positive. Okay, so now think about what we know. So what does decreasing concave up look like? I know that decreasing concave up looks like this. And then what does increasing concave up look like? Increasing concave up, I know, looks like this. Where does that transition happen? It happens at x equals 2. So I can actually kind of just sketch this thing. If I find f of 2, so f of 2 is 4 minus 8 is negative 4 plus 3 is negative 1. So I know that my curve will look like this, where this is 2, negative 1. And usually, so curve sketching, I don't know, curve sketching to me seems less important than it used to be, because calculators or computers can just graph things for us. So usually I don't even bother with more details than that. That's what this curve basically looks like, which is exactly what I was expecting. A really interesting thing that you may have noticed, may have picked up on, is if we had a generic quadratic, y equals ax squared plus bx plus c, and we find y prime, we'll get 2ax plus b. And if we set that equal to 0 and solve, we'll get x is the opposite of b over 2a, which at some point in your life you probably memorized as the x-coordinate of the vertex of a quadratic. And there it is. Calculus can give it to us without us actually memorizing it, which is another kind of cool thing. So I'm going to say that that problem is done, because that's really the level of detail that I go into with these. Let's take a look at this next one. So f of x is sine of x only between 0 and 2 pi, which is fantastic. So we're going to need f prime, f double prime, some sign charts. Let's do this. So f prime, the derivative of sine, I know because I memorized it, is cosine. The derivative of cosine for f double prime is negative sine, which again I know because I memorized it. All right, so now I'm going to say, because I memorized it a lot here, f prime equals 0. That happens. So I'm thinking of the unit circle, which I memorized, and I get x is pi over 2 or 3 pi over 2. Okay, now I'm going to think of negative sine. So if negative sine equals 0, then x is, so at 0, sine is 0. At pi, sine is 0. And then at 2 pi, sine is 0 again. So you don't get a lot of zeros for this. That's okay. Let's do a sign chart. So for f prime, I have to put pi over, so it should start at 0 and end at 2 pi. And then I have to put pi over 2 and 3 pi over 2. So it's kind of annoying. Pi over 2, because I'm not putting pi. 3 pi over 2. Okay. So it's just positive cosine. So I know what positive cosine looks like. Positive cosine is this, right? So I know that I can fill in pluses and then minuses all the way across, and then pluses. So this is for f prime, not f. And then for f double prime, I'm going to put just pi, and it should end at 2 pi and start at 0. I know what negative sign looks like also. Negative sign looks like this. So I know that I'm going to be negative and then positive. Because we're really talking about the y values of these functions that we sketched over here, right? So negative, then positive. All right, so what does this mean? On the interval from 0 to pi over 2, 0 to pi over 2, f prime is positive, f double prime is negative, so that's increasing and concave down. So increasing concave down, I know looks like this. Decreasing concave down between pi over 2 and negative pi, I know looks like this. Decreasing concave up from pi to 3 pi over 2, I know looks like this. And then increasing concave up, I know looks like this. I know people are going to if people watch this and they decide to comment, they're going to comment like, oh, you already knew what sine and cosine look like, so like you can't do this because it's circular reason. I don't care. I'm trying to like see if I know how to apply the things that I have learned. And by doing that, yeah, I had to use some other things. But yeah, obviously we know how to graph sine. We're trying to see like, how does it relate to the first derivative? How does it relate to the second derivative? Hold your comments. We don't need them. All right, let's see. So here to here. And then like I need to find the values of the function, but like we know the values of them, right? So there's a maximum at pi over 2, there's a minimum at 3 pi over 2, and then there's a point of inflection at pi, which is maybe the first time we've really talked about that for this. So 2 pi and pi, what is this? 3 pi over 2 and pi over 2. I've noticed it's when I get really close to the edges, it starts like going a little weird on me. So I happen to know the max and min or 1 and -1. So we're going to start at 0 and then increasing concave up. Sorry, increasing concave down. What? Totally wrong. Increasing concave down. Decreasing concave down. Decreasing concave up. And increasing concave up. And there you go. That's your graph. So that's from using calculus, right? So it turns out that the points where a sinusoid, a sine or a cosine, intersect its sinusoidal axis, those are going to be the points of inflection. So you can like, store that away in your brain and know that, but it's a useful fact. And so the calculus is working for us. So let's see if we can use it on this. I'm really not happy about having to find y values for this function. So hopefully they happen at like nice places, but I don't know if that's true. So f prime is going to be x squared minus x minus 2, which we can factor. Okay, so we can find the critical points, 2, -1, good enough. F double prime is going to be 2x minus 1, which if I guess I'm finding where that's 0. That'll be at 1/2. Let's say this was 0. That's at -1 and 2. So I mentioned at some point with cubics and the maximums, minimums, the x coordinates of those, and the points of inflection, like there's some kind of averaging thing going on there. -1 plus 2 is 1 divided by 2. It's 1/2. It has a lot to do with the fact that the derivative of a cube, it has everything to do with the fact that the derivative of a cubic is a quadratic. A quadratic always has its vertex at the average of its intercepts. So like think about that because it's kind of an important thing. So I definitely do not want to find the y values associated with this. So like I might not. But what I will do is sign charts. And so you have to make sure your sign charts are lined up relative to each other, right? So -1 on this one should be the same as -1 on the other sign chart, but I'm not going to put -1 because it didn't show up. Only put things that actually show up, which means if 0 doesn't show up as a 0, do not put it on your sign chart. I see that way too much. I think it's like hammered into your head maybe in like 3rd grade or something, like you should always have 0 on your number lines, but don't do that. And then 1/2. All right, so if I go back to my first derivative, so I'm looking at this basically, that's a quadratic that opens up, right? So it's going to go positive, negative, positive, positive, negatives, and then positives. And then if I look at the second derivative, so the second derivative here, to the left of -1, so sorry, to the left of 1/2 at like -1 billion, I get a negative. So a lot of negative signs to make sure that I cover all of the intervals, and then it'll change positive. So a lot of positive signs to make sure that I've covered all the intervals. Now just look at our number lines. Look at the sign charts. So from -infinity to -1, the function will be increasing concave down because the derivative is positive, the second derivative is negative. So increasing concave down looks sort of generally like that. And then we'll change to decreasing concave down because the first derivative is negative, the second derivative is negative. So then it'll look kind of like this. At x equals 1/2, we're going to change to decreasing concave up, which kind of generally looks like this. And then at x equals 2, we switch to increasing concave up, which looks like this. Now our job is to just get things in the right places, right? So I really need to know, for this to work perfectly, I need to know f of -1, I need to know f of 2, and I need to know f of 1/2. So I could use synthetic substitution, which like would work and not be terrible, but what I'm gonna use is a little bit of calculator substitution. Just switch over to a calculator. I'm gonna start a new document. I'm gonna store my function. So it's 1/3 x cubed minus 1/2 x squared. This would be like, I don't know, maybe you have the sort of teacher who lets you use a 4-function calculator. None of my students have that kind of teacher, but maybe you do. And f of -1, okay, f of 2, f of 1/2. Okay, so we got 25/6, 20, I have trouble saying that, 25/6, 25/6, I don't know, -1/3 and 23/12. Okay, let's go back to the notes and like sketch this thing. So all we're interested in is a pretty okay sketch. I don't even know what I'm going to do with these values, honestly, now that I found them, but I'm glad I used a calculator for it. So I know that I need something that goes like this, 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 right? And I know that this point right here is going to be at -1, 25/6. I know that this point right here is going to be at 1/2, 23/12. And that this point right here is going to be at 2, -1/3. Like, could I do a better job? I guess, but like I could put in axes, whatever. But like this conveys the shape of the curve, and calculus is really about shapes of curves. The like notion of finding the actual values of the function, that's more of an algebraic idea. And like to finish a lot of problems, you need the values. But you know, we're about approximating values, not finding exact values. All right, so let's do this one. It's the last problem on the page, so I guess obviously this will be the last one we do. So let's see. And hopefully it's not that bad. I mean, it's 4th degree. In my mind, I have a notion of what a 4th degree looks like. It looks like a quadratic that has like an extra hill. So 12x cubed, not excited about that, minus 24x squared plus 12x. So maybe not that bad. F double prime. Usually you want to go straight to F double prime before you like get into factoring. 36x squared minus 48x, ooh, plus 12. Okay. Okay, let's do this. 12x, and then we got x squared minus 2x plus 1. Okay, that's not that bad. 12x, then x minus 1 squared. That looks gross. Should I erase all that? You know what I'm gonna do? I'm gonna cut it because it like will never look good if I try to erase. Cut that, x minus 1 squared. Okay, and then, so I can find the zeros of that. In fact, let me do that. If this equals 0, I get x is 0 and x is 1, which is a double root, which means there won't be a sign change there. And then here I'm going to take 12 out, and I get 3x squared minus 4x plus 1. So I got to factor that. 12, 3x and x will give me 3x squared. And then -1 and -1 will give me +1, -1, -1. I also, in my mind, I was thinking that x minus 1 would be a factor because it's a double root of the first derivative, and usually those are single roots of the second derivative. Not always, but usually. No, well, maybe always. I don't know. I don't want to make a definitive statement on that. If this is 0, then x is 1/3, or x is 1. So I don't want to deal with that 1/3 because that seems terrible. Maybe I won't. No, I'm definitely going to have to. That's definitely a point of inflection. All right, sign chart. I'm going to do the sign chart over here so that I can like fit them. So f prime, f double prime. Okay, so 0 and 1, 0 and 1, and then 1/3 and 1. So 1/3 and 1. Okay, and we're testing in here because it's the most factored form that I have for f prime. So negative will give me a negative times a positive, so negative. A positive will just give me a positive, so it's going to go positive straight across. So 1 showed up a little bit early to the party is how I tend to think of that. Like it's a 0 the derivative, but there's no sign change. But then on the second derivative, probably is a sign change. So we're looking at this to test here. So negative a billion is going to be negative times negative. So that's positive. You want to make sure you get things in each of the regions, right? So 0 to 1/3, you got to have some symbols there, which is why I'm cramming them all in. And then, I don't know, it's a quadratic that opens up, right? So it's going to go positive, negative, positive. So negatives, or you test like 0.99, something like that. Is that helpful? Yeah, that's helpful because then you get like 3 minus 1 basically, and you get a negative. So you get your negative overall, and then positive, just test a billion. All right, so what does this look like generally? I have decreasing concave up, which looks like this. I have increasing concave up. I have increasing concave down. I have increasing concave up. Okay, so I think that my function, when I put all of that together, is going to look like this. Lost it. Oh man. It's the one like flaw in this thing is you can't, any continuous line when you go to erase will erase the entire continuous line instead of like little pieces of it. Other programs that I've used like will let you kind of do other things. So 0 is the minimum. So this point right here is going to be at 0 comma, what is f of 0? 1. I really don't want to find the other ones. I need 1/3. Nobody's plugging 1/3 in there. So this first point of inflection, which is kind of like here, is going to be at 1/3 comma f of 1/3. And I'm not going to find that, but that's where it is. And then the other point of inflection, the other time that the second derivative has a sign change, is at x equals 1. So x equals 1 is one of those really interesting points of inflection. It's 1. I'm not even going to find that. There is a horizontal tangent line there. It's like a weird one, right? So you get this horizontal tangent line that just kind of goes straight through your function. So it goes horizontal for like one brief moment, one instant, and then just carries on. So you don't have a max or a min, you just have like, it's a stationary point because the first derivative is equal to 0. So it like pauses, it's stationary for that one instant, and then it keeps going. All right, I think that's pretty good. And I am going to stop this video here and come back in the next video and keep going. So we are making a lot of progress. I hope you are learning a lot, and I hope you're asking questions and thinking and just generally sort of maybe enjoying these a little bit, but I will see you in the next video.